When a continent-scale power grid enters deep winter, it hits a thermodynamic wall. Heating demand spikes while solar and wind availability drop, creating systemic deficits. Deep decarbonization relies on terrestrial wind and solar, but their intermittency requires immense, long-duration energy storage. As grid penetration increases, the cost of batteries and hydrogen reserves needed to bridge these gaps scales exponentially. To calculate the limits of this approach, researchers use the PIPSA-Your capacity expansion model. This framework is the mathematical standard for optimizing the European power grid across millions of potential variables. When this model evaluates a capital-intensive space-based solar power project, it yields a paradox. Integrating orbital generation reduces total European system cost by 7 to 15%, while cutting battery usage by over 70%. To solve the economic penalty of terrestrial scaling, grid architects are now evaluating the mathematical viability of putting baseload generation in orbit. We are deconstructing the exact techno-economic thresholds where space-based solar power shifts from a cost-prohibitive concept to a grid-dominant asset. This transition depends on the architectural bottleneck between active heliostat reflectors and fixed planar designs. We will also examine recent empirical breakthroughs in microwave and optical beaming hardware that are transitioning these systems from theory to physical reality. Space-based solar power provides a rigorously quantified economic pathway for future grids, shifting the focus from aerospace theory to measurable infrastructure. A standard terrestrial solar panel has an annual availability factor of roughly 15 to 30%. Atmospheric scattering, weather, and the Earth's rotation ensure its output remains inherently variable. The systemic advantage of an orbital system is availability. Operating in geostationary Earth orbit, 36,000 kilometers up, bypasses atmospheric attenuation and the day-night cycle. Altitude alone does not guarantee continuous power. NASA's mature planar array architecture is limited by gravity gradient forces. Because its transmission antennas must remain locked toward Earth, its solar panels cannot maintain optimal sun-facing angles, capping its availability at 60%. Contrast this with NASA's Heliostat Swarm. Active mirror tracking continuously focuses sunlight onto a central concentrator, achieving a near baseload availability of 99.7%. This 2050 simulation tracks weekly power output. The heliostat design, the red line, delivers a flat, consistent 300 to 350 gigawatts. However, the partially intermittent planar architecture proves economically unviable, as its variability fails to offset the terrestrial storage required for grid balance. Only the continuous profile of the heliostat design displaces enough terrestrial intermittency to justify the massive initial capital expenditure of the launch. Grid-level viability is strictly dictated by the specific mechanical architecture utilized to collect sunlight in orbit. Beaming gigawatts of energy from orbit to a grid requires a solution for lethal scattering and precision. In 2023, Caltech's MAPLE experiment validated the core physics in orbit, successfully beaming detectable power to Earth using a flexible, lightweight microwave array. MAPLE uses timing control elements to create constructive and destructive interference. By overlapping electromagnetic waves so they cancel out in some areas and amplify in others, the system forms a directional energy beam without moving parts. Ground tests are now scaling this complexity. ZDN University's Omega system recently demonstrated one-to-many dynamic transmission, tracking, and powering multiple moving targets simultaneously. The Omega project delivered over 1,000 watts over 100 meters to moving drones, maintaining a direct current-to-direct current efficiency of 20.8%. Other developers are pursuing optical frequencies. Starcatcher Industries recently set a record, delivering over 1.1 kilowatts of electrical power using multi-wavelength lasers. These optical systems have secured power purchase agreements for orbital data infrastructure, transitioning into commercial application. The physics of targeted energy transmission are empirically validated. The remaining barrier is scaling system economics. Space solar does not need cost parity with terrestrial panels because it serves a different grid function. It provides the balancing stability that intermittent sources lack. When heliostat capital costs fall to 14 times the 2050 cost of terrestrial solar, they hit a complementary threshold. At this 14x level, orbital generation displaces short-duration grid batteries and pumped hydro storage. As costs drop below 9 times the terrestrial benchmark, Space solar flips from a complementary asset to the dominant baseload generator on the European grid. This scaling reveals a storage paradox. While total battery usage crashes by 78%, hydrogen storage behaves differently. Between the 14x and 11x cost thresholds, the capacity required for long-duration hydrogen storage surges to 178% of its baseline. Near baseload generation from orbit eliminates the need for daily, short-term balancing, driving the collapse in battery demand. However, European winter demand spikes outstrip baseload capacity. Mechanical hydrogen storage is required to buffer remaining multi-month deficits. Space solar solves the daily intermittency curve, while hydrogen solves the seasonal intermittency curve. Building high-voltage direct current lines across Europe involves massive physical footprints and the bureaucratic complexity of routing power through dozens of sovereign states. Centrally coordinated satellites function as distribution hubs, switching energy targets near instantly to meet localized demand across the continent. Integrating this orbital capability reduces the need for long-distance terrestrial DC transmission lines by 31 to 70%. These satellites operate as orbital grid interconnects, distributing power with the agility of a digital switchboard. By replacing ground-based wires with wireless microwave beams, space solar physically shrinks the terrestrial infrastructure required for a net-zero continent. Reaching the 9x to 14x economic thresholds requires a specific development roadmap. The focus must move beyond proving beaming physics and toward establishing modular, autonomous in-orbit manufacturing. Reducing launch mass and orbital payload costs is the absolute necessity for making the capital expenditure viable. These aerospace hurdles must be weighed against the geographic reality of trying to power a continent using only surface-level generation. Space solar power is a rigorously quantified techno-economic pathway to bypass the geographic and storage limits of terrestrial decarbonization.